All right, let's jump into this quantum mechanics book.
Yeah, let's do it.
A deep dive into all things quantum.
I'm excited.
Me too, and it's not exactly like reading a novel.
Yeah.
It's a pretty dense textbook, but
Yeah, we're going to try to break it down, make
yeah,
it a little bit more approachable.
exactly. And we've been talking a lot about this, and I think we're going to try to highlight some of the things that really blew our minds.
The aha moments.
Yeah, the things that finally made it click.
Exactly.
Like, oh, okay.
Yeah, and I'll be chiming in with the so what? Like, why?
Yes.
Why does any of this matter?
Yes.
Not just for physics, but like how does it relate to the listener's life, potentially their work?
Yeah, absolutely. I love that.
Yeah.
So we're starting with chapter 1, the origins of quantum physics, and it's really like discovering a hidden code to the universe.
Oh, I like that.
Like it's incredible. And so we start with this thing called black body radiation, which I never even really thought about. You see like a hot object, like a stovetop,
Right.
that's glowing, and it's like, well, why is it glowing that color?
Right. Why is it glowing at all?
Yeah, and classical physics had a hard time explaining that.
Yeah, it really did.
So Max Planck comes along and he's like, what if energy isn't this smooth, continuous flow? What if it's like a vending machine that only takes certain coins?
Okay. Yeah.
Like you can't put in a $1.75 for a snack.
Right.
It's like $1 or $2, and that's quantization.
Right. It's that idea that it's discrete. It comes in these chunks.
Exactly, and that was revolutionary.
It really was like discovering the world is made up of pixels instead of this smooth, continuous image.
Yeah, I love that.
Right. Like it's quantized. It's discrete. It's not just any value. It's specific values.
Yeah, it's like mind-blowing. And then that led to other discoveries like the photoelectric effect.
Oh, yeah. The photoelectric effect. That was huge.
It's like when you shine light on metal, and sometimes electrons pop off, but only if the light's frequency is high enough.
Exactly.
It's like needing a specific key to unlock a door.
I like that. Yeah.
Like you can jiggle that low energy key as much as you want.
Doesn't matter how many times.
It's not going to unlock.
Right.
But that specific key.
The right frequency,
Yeah.
the right energy unlocks the door.
Exactly. And Einstein explained this by saying that light itself is quantized.
Right.
It comes in these packets called photons.
Yeah, that was a big deal.
And this is like, it's not just theoretical. This is how solar panels work.
Right, exactly.
It's like, wow.
It's like the foundation of so much modern technology, like
Yeah.
solar panels, digital cameras. They all rely on this quantized nature of light.
Yeah, it's incredible.
It's amazing. And, it also proves this idea of particle-wave duality.
Oh, yeah.
Light acts like a wave sometimes. Sometimes it acts like a particle.
Right. It's like, how can it be both?
Right. It's mind-blowing. It really is.
Yeah. And then we get into the Compton effect, which is, it's wild.
It is wild.
It's like when photons act like these tiny little billiard balls
Yeah.
and they're bouncing off electrons.
But here's the thing.
Yeah.
They don't always bounce off the way we'd expect.
It's like defying the laws of physics that we thought we knew.
Right, exactly.
But it's like if you imagine a bowling ball hitting a tennis ball,
Yeah.
and instead of flying off in a predictable way,
Yeah.
it goes off in this crazy angle.
Right. It's like, what just happened?
What?
And, the Compton effect just provided even more evidence for the particle nature of light.
Right.
But what's even more mind-blowing is that in these bizarre interactions,
Yeah.
the fundamental laws, like the conservation of momentum and energy, they still hold.
Okay, so there's some order to this chaos.
There's a method to the madness, yeah.
Okay, I like that.
It's like the universe has these underlying rules even when things get really weird.
I can handle that, but are you ready for this?
Hit me with it.
Louis de Broglie comes along, and he says, what if matter?
Wait a minute.
Like electrons, protons, you and me,
Okay.
have wave-like properties too.
What? What?
That's crazy.
It's like saying a baseball can act like a ripple in a pond.
Right. It's like, how is that even possible?
It's mind-blowing, but experiments later confirmed it.
It's true. It's true. And you know what's even more amazing?
What?
Is that this wave-particle duality, it's not just a theoretical thing.
Yeah.
It's the foundation for things like electron microscopes,
Oh, wow.
which allows us to see things at the atomic level.
That's incredible.
Right. So this crazy idea has real-world implications.
Yeah, it's amazing. And then there's the double slit experiment,
Oh, that one's a classic.
which it really messes with your head.
It does. It does.
You fire these electrons one at a time through two slits.
Okay.
If they're particles, they should go through one or the other.
Right.
But they create this interference pattern.
Like a wave.
Like a wave.
Right.
How is that even possible?
It's the mind-boggling concept of quantum superposition. Okay, break that down for me.
All right, so the electron doesn't choose one slit or the other.
Yeah?
It's in a superposition of states, meaning it's kind of going through both slits at the same time
It's like it can be in two places at once.
until we try to measure it.
Okay.
Then it collapses into a single state.
So it's like a coin spinning in the air,
I like that.
and it's both heads and tails until it lands.
That's a great analogy.
So to wrap up chapter 1, it's like energy and light are quantized, particles can act like waves, and the act of observing something can actually change it.
It's a lot to process, I know.
It is. It's heavy stuff.
It is, and it raises some pretty profound questions.
Like what?
Like if even solid matter, things like electrons, have wave-like properties.
Yeah.
What does that say about the nature of reality itself?
It's like, what are we even made of?
Right, it's like, what is reality?
All right, so get ready, because next we're diving into chapter 2, the mathematical tools of quantum mechanics. Now, I know math can be intimidating, so we're going to focus on the concepts, not the equations.
Sounds good.
Okay, so imagine vector spaces like a recipe.
A recipe.
You could adjust the amounts of each ingredient.
Okay.
And in quantum mechanics, these ingredients represent the states of quantum systems.
Okay, so the vector space is like the framework
Exactly.
for describing these quantum states.
Right, and the math isn't just about crunching numbers.
Right.
It's a language.
Yes, it's a way to represent and manipulate these quantum states.
I like that. And one key tool is Dirac notation.
Bracket notation.
Yes.
Yeah, it's a shorthand way to write down these states and how they interact.
Okay, and then we have the postulates of quantum mechanics.
Ah, the postulates.
The ground rules of this quantum game.
They're like the fundamental principles
Exactly.
that govern how quantum systems behave.
Right. They tell us how to represent states.
How to represent things like position and momentum.
And how measurements work in this fuzzy world of probabilities.
Yeah, it's not like classical physics where everything is nice and deterministic.
Right, everything's a maybe.
Right, it's all about probabilities.
Yeah, and of course we can't forget those quantum mechanical operators.
Oh, the operators, they're like the tools of the trade.
Yes, they're like mathematical machines that act on quantum states.
Exactly. We've got the position operator, the momentum operator, the Hamiltonian, which represents the total energy.
And the angular momentum operator, describing rotational motion.
It's like a whole toolbox of mathematical gadgets.
I love it. And one of the mind-bending consequences is the Heisenberg uncertainty principle.
The uncertainty principle, that's a classic.
It says that we can't know both the position and momentum of a particle with perfect accuracy.
At the same time.
Right? It's like trying to nail down a shadow.
I like that. The more you focus on one,
Yeah.
the blurrier the other becomes.
It's like you can't have it both ways.
Right. You can know one precisely.
Yeah.
But then the other one becomes uncertain.
This is a trade-off.
It's a fundamental limit to what we can know.
And finally, we meet the time-dependent Schrödinger equation.
Ah, the Schrödinger equation, the workhorse of quantum mechanics.
It's like a powerful equation that describes how quantum systems change over time.
It's like having a crystal ball that lets us predict the future behavior of particles.
That's pretty cool.
It is. It is.
So that's chapter 2 in a nutshell, a toolkit for navigating the quantum world.
Yeah, we covered vector spaces, Dirac notation, the postulates, those quantum operators, the uncertainty principle.
In the Schrödinger equation.
It's a lot to absorb, but it's all essential for understanding the deeper mysteries that await us.
Oh yeah, and those mysteries.
They're what make quantum mechanics so captivating.
All right, so get ready, because next we're going even deeper, exploring the postulates in more detail, tackling the measurement problem, and encountering even more mind-bending concepts.
Let's do it.
All right, chapter 3, the postulates, the heart of quantum mechanics.
The fundamental law.
Yeah, how quantum systems behave. So the first postulate says a system's state is completely described by a wave function,
The blueprint, all the information we can know.
like a recipe for a quantum cake.
I like that.
It tells you the exact amounts of each ingredient.
The probabilities of finding the system in various states.
Right, and then the second postulate says for every measurable quantity, there's a corresponding operator.
Like position, momentum, energy.
Those operators we talked about in chapter 2, not just symbols.
Right, they represent physical quantities, things we can measure.
And the third postulate says when we measure an observable result hour, the only possible results are the eigenvalues of the operator. So if we're measuring energy,
Right.
we can only get specific energy values, not a continuous range.
It's like a staircase. You can only step on the steps, not in between.
I get it. The fourth postulate gets into probabilities.
Right.
The probability of measuring a particular eigenvalue is related to the overlap between the wave function and the eigenvector.
So we can't say for certain what the outcome will be, but we can calculate the probabilities.
It's like predicting the weather.
Ah, good analogy.
We can't say for sure if it will rain,
Yeah.
but we can give you the odds.
Exactly.
The fifth postulate, the wave function evolving over time.
Governed by the Schrödinger equation.
It's like a movie director shouting action.
Yeah. Tells the wave function how to change, how to evolve.
Gives us a glimpse into the dynamics of the quantum world.
It's like a sneak peek behind the scenes.
And then this crazy thing.
What?
Measurements actually change the system.
Yeah, the measurement problem.
It's like observing something alters it.
We could talk about this for hours.
I know, right?
So before we measure it, a system can be in a superposition.
Multiple states at once.
Right. But when we measure it,
We force it to choose one.
like a spinning coin finally landing on heads or tails,
So before we measure it,
it's a blurry cloud of possibilities
and the measurement collapses that cloud.
into one definite state.
Wow, okay. And then compatible observables.
Quantities we can measure simultaneously without affecting each other.
But then there's the uncertainty principle.
We can't know both position and momentum with perfect accuracy
A fundamental limit.
baked into the universe.
The complete sets of commuting observables. CSCOs,
Sets of observables that completely define a system's state.
like having all the pieces of a puzzle.
You can assemble the complete picture.
Okay, on to chapter 4. One-dimensional problems.
Taking those abstract postulates and putting them to work.
Solving problems in one dimension.
Like a particle trapped in a box.
So first, general properties of motion in one dimension.
How does a particle behave when it encounters a higher potential energy region?
Like a ball trying to roll over a hill taller than it is.
Where classically it would roll back down.
But quantum mechanically.
There's a chance it could tunnel through.
Quantum tunneling.
It's like a ghost passing through a wall.
So cool. Then bound states. A particle confined to a region.
An electron bound to an atom trapped by the nucleus.
Like being stuck in a well.
It can't escape unless it has enough energy.
And scattering states. The particle is free to move.
A comet zipping through space, not bound to anything.
A wild horse running free.
I like that.
So chapter 4 covers all these potentials.
The free particle, the potential step, the potential barrier.
The finite square well, the infinite square well.
Let's start with the free particle. No force is acting on it.
Like a ball rolling on a perfectly flat surface.
The solution is a plane wave, extending infinitely.
A ripple in a pond just keeps going.
Exactly.
Then the potential step, a sudden jump in energy.
Like hitting a wall.
Part of the wave function is reflected, part transmitted.
A wave hitting a rock, some bounces back, some keeps going.
The potential barrier, a region of higher energy.
Like a wall the particle needs to climb.
Classically, if it doesn't have enough energy, it can't cross.
But quantum mechanically, it can tunnel through.
Mind-blowing, like a ghost passing through a wall.
And it has real-world applications, transistors, microscopes.
Okay, the finite square well, a well with a finite depth.
It can be trapped, but it could escape if it has enough energy.
And the infinite square well, infinitely high walls.
Completely trapped.
The solutions for both are standing waves, like vibrations in the guitar string.
Right. Confined to the well.
And then the harmonic oscillator.
Describes so many physical systems.
Vibrating molecules, oscillations of atoms.
Shaped like a bowl, a parabolic potential.
The solutions are equally spaced energy levels.
Like rungs on a ladder.
The spacing determined by the frequency.
Right. Higher frequency, wider spacing.
And then parity, symmetry of the wave function,
Is or odd?
affects its behavior under transformations,
It can tell us which transitions are allowed,
like a traffic light.
regulating the flow.
And lastly, numerical methods for solving the Schrödinger equation,
Using computers to find approximate solutions.
simulating quantum systems.
It's like having a virtual lab.
So chapter 4, one-dimensional quantum problems.
From the free particle to the harmonic oscillator,
Now chapter 5, angular momentum.
a deep dive into this fundamental quantity.
Classically, it's about spinning objects.
TOPS, planets orbiting the sun.
But in the quantum world,
It's still about rotation, but it's quantized.
so not just any spin,
It comes in discrete values.
like a dial that clicks.
And the angular momentum operator is key.
It always seems to come back to that.
It's the heart of rotational transformations.
So chapter 5 starts by defining the orbital angular momentum operator,
Describing the angular momentum due to motion around a central point.
the quantum version of classical angular momentum.
For an electron orbiting a nucleus.
It describes its motion.
And this operator commutes with the Hamiltonian for a central potential.
So we could measure them simultaneously.
Right, angular momentum is conserved under a central force.
Like a figure skater pulling in their arms to spin faster.
Perfect analogy. The angular momentum stays the same.
Even though the speed changes.
And then Chapter 5 explores the commutation relations.
So how the different directions of angular momentum are connected.
We can't know all three components precisely at the same time.
A Heisenberg uncertainty principle for angular momentum.
Exactly. The more you know about one, the less you know about the others.
Then we get to the eigenvalues and eigenvectors.
The possible values of angular momentum and the corresponding states.
And guess what? They're quantized.
Just like those energy levels.
Angular momentum comes in discrete packets.
And then spin angular momentum.
This intrinsic angular momentum particles have, even when they're not rotating.
Like an inherent property, like mass or charge.
So even if an electron is still, it has spin.
That's right.
And it's quantized too.
Of course, it's the quantum world.
It's like every particle has a tiny spinning top.
And we can only measure it in specific increments.
And this spin is important.
It's crucial for understanding magnetism and how particles interact.
All right, so it's not just theoretical.
It shapes how our world works.
Amazing. Then total angular momentum.
The sum of orbital and spin.
Combining spins, but not a simple addition.
We use those Clebsch-Gordon coefficients.
A recipe for combining spins.
Tells us the possible values and states.
Like mixing colors of paint.
You get new colors depending on the proportions.
I like that. And then Chapter 5 wraps up with real-world applications.
Like the Zeeman effect.
What's that again?
Splitting of atomic energy levels in a magnetic field.
Because of the interaction between the atom's magnetic moment and the field.
And that moment is related to its angular momentum.
So we apply field, energy levels split, and it's tied to angular momentum.
A magnifying glass for subtle energy differences.
Chapter 5, a deep dive into angular momentum.
Properties, eigenvalues, eigenvectors, spin, total angular momentum.
Addition of angular momenta, applications.
Ready for Chapter 6.
Bring it on, 3 dimensions.
Three-dimensional problems building on what we've learned.
From flat land to the real world.
It gets more interesting.
I bet.
Especially central potentials depending on the distance from a central point.
Like gravity or the attraction of a nucleus.
We'll learn to solve the Schrödinger equation for this.
And we'll switch to spherical coordinates.
They sound exotic.
A little bit.
But they're natural for spherical symmetry.
Like using latitude, longitude, altitude on Earth.
And the angular part of the wave function is described using spherical harmonics.
3-dimensional waves.
Capturing the angular dependence.
So Chapter 6 covers all these examples.
The free particle in 3D, the box potential, the spherical square well.
The isotropic harmonic oscillator, and the hydrogen atom.
The hydrogen atom, one of the most important systems.
Finally, we get to tackle it.
We'll see how those quantum numbers arise.
And where those energy levels come from.
It all comes together.
So the free particle in 3D, how is it different?
The wave function depends on all 3 coordinates.
More complex.
And it's a plane wave traveling in a specific direction.
Like a wave rolling across the ocean.
Exactly.
The box potential in 3D, like the infinite square well, but in a box.
From a flat land prison to a 3D one.
And the solutions are still standing waves.
Trapped inside.
What about the spherical square well?
A particle trapped in a spherical bubble.
With infinitely high walls?
Potential is 0 inside. Infinite outside.
A quantum bouncy ball in a force field.
And the solutions involve spherical Bessel functions.
Okay, the isotropic harmonic oscillator. Potential is the same in all directions.
Like a marble in a spherical bowl.
Solutions involve Hermite polynomials and Gaussian functions.
A bit more complicated.
All right, the hydrogen atom.
The main event.
A two-body problem. Electron orbiting a proton.
But we can treat it as one particle with a reduced mass.
Like combining the Earth and Moon.
The potential becomes the Coulomb attraction.
And we solve it using spherical coordinates.
And the solution is beautiful.
Quantized energy levels, matching experiments.
We've cracked the code.
Those spectral lines, they come from the quantized energy levels.
Each line a jump between levels.
And the color tells us the energy difference.
Amazing, right?
Chapter 6, a journey through 3 dimensions.
Free particle, box potential, spherical square. Well,
Isotropic harmonic oscillator, hydrogen atom.
using spherical coordinates.
Now Chapter 7, rotations and addition of angular momenta.
Taking our understanding even further.
Bring on the rotations.
Yeah.
Okay, Chapter 7, rotations, how they affect quantum systems.
It's not just about particles spinning.
Yeah, we're talking about rotating whole systems.
Like flipping a molecule, a tiny solar system.
Wow.
We use these special rotation operators to describe these transformations.
Okay.
And here's the thing. angular momentum is tied to these rotations.
It always seems to come back to angular momentum.
It's the driving force behind these rotations.
So if we understand angular momentum,
We understand how a system behaves under rotation.
I like that.
And then there's the addition of angular momenta.
Okay.
You have two particles, each with their own spin and orbital angular momentum.
Yeah.
How do we combine them to get the total angular momentum?
Is it just adding them up?
It's not that simple.
Okay.
We use Clebsch-Gordan coefficients.
What are those?
They tell us the possible values of total angular momentum and the corresponding states.
So it's like a recipe for combining spins.
Exactly.
Even if the system has many particles?
It's crucial for analyzing atoms with multiple electrons.
Right. They each contribute to the total.
Exactly.
Okay. Tensor operators.
They sound intimidating.
Yeah.
But think of them as operators with multiple components
Okay.
that act in a coordinated way when you rotate the system.
They represent more complex interactions,
Like electric dipole or quadrupole moments.
describing how a system interacts with external fields.
Exactly.
Okay, and the Wigner-Eckart theorem.
A powerful tool for simplifying calculations.
How so?
It separates the geometric aspects from the physical details.
What shortcut?
Exactly. It helps us focus on the essential physics.
Okay, chapter 8. Identical particles,
Particles that are truly indistinguishable.
like identical twins.
Exactly.
You can't tell one from the other.
Even in principle.
Wow.
And this has huge consequences for systems with multiple particles of the same type.
What kind of consequences?
Well, it leads to the Pauli exclusion principle.
Okay,
No two identical fermions can occupy the same quantum state.
back up. Fermions.
Particles with half-integer spin.
Okay, like electrons?
Exactly. Protons, neutrons,
I'm bosons.
integer spin, like photons.
Got it. So no two electrons in the same state.
It's the bedrock of chemistry.
Wow.
It prevents atoms from collapsing.
So it's not just a theoretical quirk.
It shapes the structure of matter.
Then symmetric and antisymmetric wave functions.
Symmetric doesn't change sign when you swap particle labels.
Okay.
Antisymmetric flips the sign.
Like musical chairs with particle identities.
Exactly.
And fermions must have antisymmetric wave functions.
Bosons, symmetric.
It's different rules for swapping identities.
And this leads to different statistical behavior.
Fermi-Dirac for fermions.
Bose-Einstein for bosons.
And these statistics are important.
They explain phenomena like electrons in metals, superfluids, Bose-Einstein condensates.
Wow, this deep dive into quantum mechanics has been amazing.
We've seen how angular momentum, rotations, and identical particles
Shape the world around us.
and we've only scratched the surface.
I know, it's incredible.
Quantum mechanics is a vast field, always evolving,
But this has given us a good foundation.
and a sense of wonder.
Absolutely. Thanks for guiding us.
It's been a pleasure.
And to everyone listening, keep exploring. The quantum world is full of mysteries.
And who knows what we'll discover next.
Yeah, it's exciting.